In the last class, I was discussing questions related to whatever we have discussed up to this point. Next topic is thin film interference. So, thin film interference, basically in thin film interference, we are going to deal films here, this type of thin films. For example, suppose this type of film is there and it is deposited, ठीक है, on some substrate. Suppose this is a substrate, ठीक है, this is some substrate. So this is substrate, ठीक है, and this is thin film which is deposited over it. Thin film. Second example may be like you are having a glass plate, thin glass plate. Here you are having thin glass plate. So this is a thin glass plate. Thin glass plate. On this side you are having air, and on the lower side also you are having air. This type of situation may be there. Next, here this is air. This is air. Third, maybe like you are having water. So here you are having water. This is a water. And over this water, an oil film is spreaded. So this is water here. So this is water here. And over this water, we are having a thin film. ठीक है ना? We can have a thin film that is of oil, some oil. So an oil film is spreaded over water. So what is this? This is oil film that is spreaded over water. So this is oil film, thin oil film. Film. And here we are having air. So oil film, and this water. So this type of films we are going to deal with here in this case of thin film interference. Next question is that what is the meaning of thin film? What should be the thickness of the film so that we are going to call it as thin film? Okay. So actually we are going to call a film as thin film if thickness of the film, suppose T is the thickness, if thickness of the film, here I use this color. So if thickness of the film T is of the order of lambda. Okay, what is lambda? Lambda is the wavelength of the light that is incident over here. Okay, na? That is wavelength of the light that is incident over here. Here. So if thickness of the film is of the order of lambda, then we are going to call that film as a thin film. We are going to treat that film as a thin film. So first thing is this. So first we should know what is the meaning of thin film. So different type of thin films may be there. We are going to deal here. First, this is air, then a denser, and then next. Okay, air, then thin film here, and then substrate. So their refractive indices may be in the increasing order, or it is also possible that the refractive index of the thin film is greater than the refractive index of the substrate. Okay, so you can face this type of situation. Suppose here, for example, here this is mu a, and in between this is mu f mu film, and it will be like this. You can face a situation where mu f film thickness that is greater than the refractive index of first medium but less than the refractive index of the second medium. Okay, this is less, this is further greater refractive index, further greater refractive index in the increasing order of the refractive indices. Maybe there you may face a situation where refractive index is such that it is greater than the refractive index of the first medium. ठीक है ना? And it is and mu f is also greater than the refractive index of the substrate. This type of situation may be there. ठीक है ना? You can have this type of situation. So these various situations we can observe in case of thin film interference. So first is, what is thin film? So thin film, for the light you are using, thin film is that film whose thickness is of the order of wavelength of that light. So for thickness, for thin film, thickness of the film should be of the order of lambda, of the order of lambda. Now, in this case, in thin film interference, in thin film interference, first question is how we are going to create coherent sources. If we want that interference should occur, if we are saying that interference should take place, then how coherent sources are to be produced. So for thin film interference, remember that this is division of amplitude. Here, division of amplitude takes place. Division of amplitude takes place. And two coherent sources are produced. So by using this method, division of amplitude, two coherent sources are created. ठीक है? By this, coherent sources are produced. ठीक है? So for this, to explain it, I'm here taking a glass plate. ठीक है? I'm taking a glass plate, thin glass plate. या थोड़ा और बढ़ा लें. I'm taking, this is the glass plate, which is surrounded by, on both sides, which is surrounded by air. So this is a glass plate, thin glass plate. Thin glass plate. ठीक है? Its thickness is T. What is the thickness? Thickness of this is T. And second, what is the refractive index? That is, you can say mu f. Mu f is the refractive index of this glass plate. Okay? Now, what is going to happen? A wavefront of light is incident over here. So a wavefront is incident like this. So a part of this wavefront will be reflected back. A part of the wavefront will be transmitted into the glass plate. So here, direction of the wavefront in which it is propagating, the direction in which the wavefront is propagating is this one. It is incident obliquely on this thin film. So I draw a normal over here. This is a normal, and this is called as angle of incidence. This is angle of incidence. So what is this here? This is actually wavefronts. ठीक है ना? Parallel wavefronts. They are falling over here. Now what will happen? A part of it will be reflected back. Angle of reflection will be equal to angle of incidence. So here it should be R, but I'm writing it as I. So angle of incidence here, that will be angle of reflection, and I'm saying that is I. That is I. Okay? So it will be like this. Now, what is going to happen? A part of it here is transmitted into the glass plate. So a part of this incident wavefront, it is going to travel in the glass plate like this. So here this wavefront is going to move like this. A part is going to enter into the glass plate through refraction. So this angle, I am assuming this is R. This is R. So here what is happening? Here a single wavefront, or this single wavefront that is splitted into two parts. One part is traveling here, another part is entering into the glass plate. So whatever intensity is incident, okay? So if incident intensity is I, then a part of this intensity will be reflected. So this will be IR plus a part of this intensity is transmitted into the glass. So here its intensity will be AI, amplitude of incident wave square, equal to AR, amplitude of reflected wave plus amplitude of transmitted wave and square of this. This will be. So this is AI, AR and AT. So in this way, basically intensity is divided, but because intensity is depending upon the amplitude, that's why, ठीक है ना, we are calling it as division of amplitude. We are calling it as division of amplitude. Now, from here, from this point, what is going to happen? This is second interface. This was air glass interface. So first refraction is taking place and first reflection taking place here. And here, this is second interface. This is glass, air interface here. So if you draw a normal here like this, then this normal and this normal, they will be parallel. This normal and this normal, because this is a thin film and these two sides, they are parallel to each other. So automatically this angle will be equal to this angle and this will be R beta. How much it will be? It will be R. So from here, a part again will be reflected back. A part of it will be reflected back into the glass like this. And this reflected part again enter into the air, and this emerging here, this emerging wave, this will be parallel to this one. This is traveling parallel. So this is the first reflected light. This is the second reflected light, R2. And what is going to happen? ठीक है, light will also emerge here into the air and it will be parallel to this. So this will be like this. It will be parallel to this. And this will be, if you look at this angle is I. This angle will be I. So in this way, you are going to get this type of reflected light and you can call it as T1 transmitted light. You will call it as transmitted light. If you further consider reflection here, you can consider, then it will be like this. And again, after reflection, it will be like this. This will be T2. This will be T2. Okay? So here you are having transmitted light, here you are having reflected light. Now try to consider that this R1 and this R2, these two reflected lights, they are obtained from the same source. From the same source. Here, this is incident light or this is the source. This is incident light. Incident light. ठीक है ना? This is incident light. So these two reflected lights as well as these two transmitted light, they are obtained from the same source. So frequencies will be same and here they are moving in the same medium. So automatically their wavelengths will be same. So wavelength and frequency of these two lights, R1 and R2 reflected lights, they will be equal. And second, part difference between R1 and R2. If you find out the part difference between R1 and R2, that part difference will also be constant. It is not going to change with time, it will be constant. So part difference between R1 and R2 will be constant. Their frequencies are same, their wavelengths are same. So R1 and R2, these two wavefronts, this is a wavefront that is moving like this. This is also a wavefront that is moving like this. They are going to interfere and they are going to superpose and they will produce the interference pattern that is localized into this glass plate. ठीक है? They are moving parallel. So these two wavefronts which are moving parallel in the same direction, they will overlap, they will superpose and form the interference pattern. So first I will show you how the part difference between R1 and R2 will be equal. Okay? How this will be. So try to understand this. If I draw a perpendicular from here, I'm drawing a perpendicular from here, so this is 90° here. Try to understand why I'm drawing a perpendicular, because if you draw a perpendicular here, this is also 90°. Okay? So after this, both R1 and R2, they are traveling same distances. So what I'm saying here, after this red line, they are traveling equal distances. So whatever part difference is there, that is before this line. So I draw a perpendicular here so that ठीक है ना, I can justify that after this line, R1 and R2, they are traveling same distances in air. So this path and this path, they are not going to create any part difference or phase difference. So whatever part difference or phase difference is there, that is up to this point. So I write this point as A. I write this point as B. This point is C. This is D. And here, just I'm completing this one. And I'm writing this as E. This is point E. E. So can anyone tell me what will be the part difference? So I'm removing it. Can anyone tell me what is the part difference between R1 and R2? So tell me what will be the part difference. I'm writing part difference by delta. So first look here. How much distance is traveled by this? ठीक है ना? How much distance is traveled by this R2? This is R2 here. So this distance. So from here it is moving. This black line is showing the extra path that is traveled by R2. This path. So this extra path is traveled by R2. So how much it will be? This will be where it is traveling inside the glass plate whose refractive index is mu. So extra optical part traveled by R2, it will be AB plus BC. So it will be mu times AB plus BC. BC first. ठीक है? And how much extra path is traveled by this? ठीक है? How much extra path is traveled by this line? ठीक है ना? This ray R1. R1. So that is this one. This is the extra path that is traveled by R1 from here to here. And where this path is traveled in air whose refractive index is 1. Whose refractive index is 1. So I can write here minus, ठीक है ना, minus कितना? This is AD. 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 ठीक है? Please write a note here. लिखो at the first reflection, this is the first reflection here. ठीक है, लिखो बेटा. The first reflection is taking place at the glass surface. Please write. First reflection is taking place at the glass surface. At the glass surface, which is denser. Which is denser. Which is denser as compared to air. Yeah, with respect to air. That is denser with respect to air. So first reflection is taking place at the glass surface, which is denser with respect to air. So, so a phase change of pi. So a phase change of pi will take place for the reflected light R1. So a phase change of pi will take place So a phase change of pi will take place for the reflected light R1. For the reflected light R1. So if you are having a phase pi, extra phase of pi is introduced. If I convert this into the part difference, ठीक है ना? This will be 2 pi by lambda. So this will be 2 pi by lambda. This is phase difference is pi, and this will be part difference. I'm saying this is delta prime. So corresponding to pi, that phase difference that is introduced here due to the reflection in R1, corresponding part difference will be this pi is going to cancel out here, and this delta prime, it will be lambda by 2. So when you are saying that in the reflected light there is an extra phase of pi, so what this is going to have extra phase of pi. You can also say that this R1 has traveled an extra path of lambda by 2 because this pi is corresponding to a part difference of lambda by 2. You can write this. You can write this. Please write this and then say it means R1. It means R1 has traveled. It means R1 has traveled an extra path of lambda by 2. It means R1 has traveled an extra path of lambda by 2. So here, not only AD is traveled by it, but an extra path of lambda by 2 is also there. This is also there. So this will be AD plus lambda by 2. AD plus lambda by 2. ठीक है? Now look, this is I. This plus this. Try to understand this angle plus this angle is 90. And this angle and this angle is also 90. So automatically this will also be I. What it will be? This will be I beta. This is going to be I. So what will be this AD? What will be this AD? ठीक है ना? How much this will AD will be? Try to understand. This AD, if you want to write, this is AC, and this angle is I. This is 90 degrees. So this will act as a perpendicular. So what will be perpendicular? That will be AC sin I. So what will be AD? If you look at this triangle, AD will be AC sin I. ठीक है ना? This will be AC sin I. What will be AD? AD will be this one. Is it okay? ACD. Draw this. This is perpendicular. This is base. This is hypotenuse. ठीक है? So this will be perpendicular divided by hypotenuse. This will be sin I. So what will be this hypotenuse? This will be this AD, this perpendicular will be hypotenuse into sin I. So AD will be AC sin I. Why I am doing this? Because one can design many questions in this type of calculation. ठीक है? You have to understand this calculation, ठीक है ना, very clearly. ठीक है? In various exams, they can create questions where this type of calculation will be helpful. So this will be AD. Now what will be AC? AC, look at AC. This AC is this AE will be equal to this AE will be equal to this EC. So I can write it as 2AE. So I can write 2AE AE into sin I. Now I know the thickness. This is thickness T. So if AE I want to write, what will be AE upon T? If I write AE upon T, that will be this sin R, tan R, tan R. So look into this triangle. This tan R, this will be AE upon thickness T. So this will be AE will be T tan R. So this will be 2 into T tan R. And this will be sin I. This will be sin I. ठीक है ना? This will be sin I beta. Is it okay up to this point?
Yes, sir.
Now, so I can write it as 2t sine square. This will be sin R sin I divided by this will be cos R. ठीक है? Can anyone tell me here this is air and light is entering into the glass plate and refractive index is this mu f. So what will be from the Snell's law? What will be mu f? Mu f will be equal to sin I upon sin R. Sin R. So I can write this sin I as mu f sin R. So here I'm going to write mu f sin R. So this will be 2 mu f t. Sin R will be here. So this will be sin square R upon cos R. So this is second term. So first I find out AD. Now what will be AB plus BC? This AB and this BC, they will be equal. Next is AB equal to BC. First thing.
सर
Yes, beta, please.
सर साइन स्क्वायर आर कैसे हो गया?
So this sin I, ठीक है ना? I will replace this sin I. Here look at this Snell's law.
यस सर,
What will be sin I? This will
ये
be
सब
mu
समझ
f
गया.
sin R. This
हम्म.
will be mu f sin R. So I substitute it here. ठीक
हम्म.
है? Mu f sin R. ठीक है? So I get this. Next is AB plus BC. They are equal. So if you look at this triangle again, this is AB. ठीक है? This is AB. And this thickness is known to me. This angle is R. So if I write this as, if I write this T upon, I'm writing here, this is T base upon, ठीक है? Base upon hypotenuse, that is AB. Then this will be cos R. So what will be AB? AB will be T upon cos R. So I can write it as T upon cos R. So what will be this term? First term, this will be mu AB plus BC. AB plus BC. That will be AB and BC are equal. So 2T upon cos R into mu F. This is mu F. So I will get 2 times mu F T upon cos R. T upon cos R. ठीक है ना? This will be. Is it okay, beta?
यस
So
सर.
this is the first term. Substitute these value, this value and this value. This is AD here. Substitute this and this value here. So this will be on the next page. I am writing delta is equal to 2 mu ft. Delta is equal to 2 times mu ft upon cos r minus that will be 2 mu ft sin square r upon cos r, and there will be minus lambda by 2 will also be there. ठीक है? This will be. So if you take cos r, then here if you take this 2 mu ft upon cos r common, then it will be 1 minus sin square r, and that will be 1 minus sin square r will be cos square r minus lambda by 2. So part difference here will be 2 mu ft cos r minus lambda by 2. So in this case, this will be the part difference. This will be the part difference, beta. Okay? This is the part difference. You have to remember this 2 mu ft cos r. At least you have to remember this. And if first reflection is taking place, where is the first reflection taking place here? First reflection is taking place here. And this is taking place at denser medium. Try to understand this is denser medium. And this is rarer medium. So that's why this extra phase of pi is introduced. This is second reflection. But second reflection is taking place here at rarer medium. This second medium where reflection is taking place, that is rarer, and this is denser. So second reflection is taking place at the rarer medium. So no extra phase of pi is there. Here you don't have an extra phase. Why you don't have an extra phase in R2? Because second reflection is taking place at the rarer medium. When light is reflected from the rarer medium, no extra phase will be introduced. Only when light is reflected back from a denser medium, only then extra phase of pi or extra path of lambda by 2 will be introduced. So here, only in the first reflection, you are having an extra phase of pi by 2 or extra path of lambda by 2 is introduced, not here, not here. So in the reflected light, we have find out what we have done. We have find out this is the path difference. So in reflected light, when you are going to observe maxima, in the reflected light, when you are going to observe maxima, when you are going to observe the bright fringe, okay, if you observe the reflected light which is coming from a thin film reflection, after you are getting from the reflection from a thin film, then you will observe colored fringes. Okay, now try to understand here, when you are observing this light which is coming, ठीक है ना, after reflection from a thin film, you are going to observe that colored fringes, red color, blue color, or some another colors you may observe in the reflected light. Suppose you are getting, suppose you are observing the red bright fringe you are observing in the reflected light. It means wavelength corresponding to red color wavelength corresponding to red color, ठीक है ना, it is interfering in the constructive way. So constructive interference is taking place in the reflected light corresponding to wavelength lambda of the red light. So if you are observing in the reflected light, if you are observing red color, it means for the red color wavelength, constructive interference is taking place, maxima is formed in the reflected light. Suppose you are getting blue light, blue color fringe you are observing. It means for blue color wavelength, constructive interference is taking place. Suppose green color is absent. I am not observing green color here in the reflected light. It means for the green color, destructive interference is taking place. It means for the green color which is not observed in the reflected light, destructive interference is taking place, or you can say minima is formed in the reflected light. So we should know that what is the condition for the maxima. So for maxima or constructive interference interference that will be observed in the reflected light. Whatever color you are going to observe in the reflected light, for the wavelengths corresponding to those colors, they should satisfy the condition of maximum. And what is the condition of maxima? Condition of maxima is that delta should be equal to n lambda. So condition is delta should be equal to n lambda here. So what will be this? Substitute here. This will be 2 mu ft, 2 mu ft cos r minus lambda by 2. And this will be equal to n lambda. ठीक है ना? It will be equal to n lambda. So condition for the maxima will be 2 mu f t cos r, and that will be equal to, this will be 2n plus 1 lambda by 2. So this is the condition of constructive interference in the reflected light. This is the condition for the constructive interference for the reflected light. Please write the wavelengths, the wavelengths which will satisfy this condition, the wavelengths which will satisfy this condition, the wavelengths which will satisfy this condition constructive interference, forms constructive interference in the reflected light, forms constructive interference in the reflected light. That is colors, that is colors, that is colors corresponding to these wavelengths, that is colors corresponding to these wavelengths will be observed in the reflected light.
Sir, to this wavelength,
That is colors corresponding to these wavelengths, that
yes,
is
sir.
colors corresponding to these wavelengths will be observed in the reflected light. ठीक है? What is the condition of minimas? Particularly those wavelengths whose colors will not be observed in the reflected light, they are forming minimas in the reflected light. So here for minimas, destructive interference, destructive interference, ठीक है, or minimas, what will be the condition? Minimas, that will be delta equal to, ठीक है ना, delta equal to, you should know that it should be lambda by 2, 3 lambda by 2, 5 lambda by 2, in this way. So how I will write? I'm writing it as 2n minus 1, 2n minus 1 lambda by 2. ठीक है? So where should this n should start? So n should, I'm writing here -1. So here this n will be 1, 2, 3, like this. But you should always remember in your mind that delta should be lambda by 2, 3 lambda by 2, 5 lambda by 2. This should be. So what is the part difference? Part difference is 2 mu t, mu ft cos r minus lambda by 2. And this will be equal to 2n minus 1 lambda by 2. So what is the advantage here? This minus lambda by 2 will cut out with this, will cut on both sides. So this will be 2 mu t, or condition will become 2 mu ft cos r equal to n lambda. But remember, this n will be 1, 2, 3, 4, not 0. This will be. So this will be the condition of destructive interference. So these are the conditions of constructive and destructive interference. लिखिए बेटा, colors please write after this. Colors
Sir,
corresponding to wavelengths. Colors corresponding to wavelengths. Colors corresponding to wavelengths. Colors corresponding to wavelengths which satisfies this condition of minima, which satisfies the condition of minima, which satisfies the condition of minima will be absent, will be absent in the reflected light, will be absent in the reflected light. ठीक है? So
sir,
basically, yes बेटा.
sir, मैक्सिमा के लिए इनकी वैल्यू भी 1 से स्टार्ट होगा, 1 2 3 4।
हाँ, n के लिए बेटा it may be, you can look here. What is the condition of n here? It may be 0 lambda. Here I can write this may be 0. This may be lambda, 2 lambda. It will be like this. ठीक है? So I'm writing this is n lambda. So n will start from 0, 1, 2, 3. But here this is lambda by 2, 3 lambda by 2. So I design another. I'm not writing 2n plus 1 lambda by 2 because I want to cancel out this lambda by 2. So I rewrite this formula as 2n minus 1 lambda by 2. But when I'm writing this formula, remember this n will be 1. If you are substituting 1 here, this will be 2 minus 1 into lambda by 2. 2 minus 1 is 1 and lambda by 2 first term you are going to get. If you place 0
यस सर।
here, then this will be minus lambda by 2. So you are not going to get correct value. Okay? So that's why. Or if you want to write it as m, you can write it as m. It doesn't matter. If you want to write it as m, this is okay. Okay? So you may also write it as m. And here m will be 1, 2, 3 like this. And here this n will be 1, 2, 3, 4. 0, 1, 2, 3. And here n,
यस सर,
that is
इसमें 0 से स्टार्ट होगा।
0, 1, 2, 3. ठीक है, but never take care of this. Don't be confused. Always keep in your mind that delta should be equal to lambda by 2 or 3 lambda
यस
by
सर।
2 or 5 lambda by 2. Then you will be very clear. So in this way. Now, one more thing here that is important. So what we are getting here, we are getting colored fringes in the reflected light due to the constructive interference. When you are going to get these colored fringes, if incident light is white light. So when white light is incident on a thin film. So here, what I am assuming, I am saying this is a white light. This is a white light button. So if white light is incident on a thin film, then in the reflected light due to constructive interference, you are going to get the colored fringes. And the colors whose wavelength is satisfying the condition of destructive interference, they will be absent here. So colors which we are observing here, they are forming constructive interference, and colors which are absent, they are forming destructive interference here. So this is one case. Now here you can also observe interference phenomena in the transmitted light also. Here you can also observe the phenomena here in the transmitted light. So I can again find out what I'm going to do here. I will again draw a perpendicular like this. And I will find out the path difference. ठीक है, I am not going to do that exercise, but that path difference again will be 2 mu t cos r. You can do this, but right now it's not required. So path difference still comes out to be 2 mu t cos r. But this time, how this transmitted light you are getting? Try to understand how you are getting this transmitted light. Look here. Just 1 second. ये दिखाई नहीं देगा. So, देखो, up to this point, ठीक है ना? This reflected light and transmitted light, they were same up to this point. From here, it is split it into two parts. One part is moving like this, another part is moving like this. Now these transmitted light, they are obtained from this part that is transmitted. This reflected light is not playing any role in the transmitted light. So look here. For this transmitted light, no extra phase is there. For the refraction, for the transmission, when light is entering into another medium, no extra phase is introduced. So it's moving like this. In this reflection here when reflection is taking place, because this reflection is taking place at the rare medium, here no extra phase is introduced. So it is moving like this. So it will move like this, move like this. And here at this point, again, light is traveling from here to here. So this is rarer medium, this is air, and this is denser. So this third reflection is taking place at the rarer medium. So no extra phase here. And light is moving like this. So here, this T2, it is not having any extra phase. This transmitted light, this light, a part of it is entering directly into the second medium as a result of refraction. So no extra phase here. So here in the transmitted light, no extra phase of pi is there. Okay, no extra phase of pi is here. So here you can observe that no extra phase of pi is present in T1 or T2. So what will be the power difference between T1 and T2? So what will be the power difference in the transmitted light? So in transmitted light, please write here in the transmitted light, in the transmitted light, T1 and T2 will act as, in the transmitted light, T1 and T2, in the transmitted light, T1 and T2 will act as coherent sources. In transmitted light, T1 and T2 will act as coherent sources. T1 and T2 will act as coherent sources. As coherent sources, full stop. No extra phase of pi will be present. No extra phase of pi will be present in the transmitted light. No extra phase pi will be present in the transmitted light. So, power difference delta in the transmitted light will be 2 times mu f t cos r. 2 mu f t cos r. For the transmitted light, this will be the power difference. This will be the power difference between. So remember this. 2 mu f t cos r. This will be the power difference. So now in the transmitted light, what will be the condition of constructive interference? Interference. This is maximum. This will be 2 mu f t cos r. This is the power difference. This will be equal to n lambda. So this is reverse condition. Whatever was the condition of minima in the reflected light, the same condition is for the constructive interference for the maxima in the transmitted light. So this is the condition for constructive interference in the transmitted light. What will be the condition for destructive? Destructive interference. Interference or minima. This will be 2 mu f t cos r. And this time this will be simply lambda by 2, 3 lambda by 2. So if you want to write here, this time this will be simply 2n plus 1 if you want lambda by 2. And here n will be 0, 1, 2. So here this n 0, 1, 2 is not important. What is important here? It should be lambda by 2, 3 lambda by 2, 5 lambda by 2. So that thing should be very clear. So what you are observing here, that conditions of maxima and minima is reversed in the reflected light. So these are the conditions of maxima and minima in the transmitted light. And in the reflected light, in the reflected light, for maxima, what was the condition? 2 mu t cos r, 2 mu t, sorry, cos r, and this was 2n plus 1 lambda by 2. ठीक है? And for minimas, this was 2 mu ft cos r equal to m lambda. This is. Now tell me one thing. Suppose in reflected light, suppose in reflected light, red color, red color wavelength is satisfying the condition of maxima. Means in reflected light, you are observing red color maxima. Red color fringe you are observing. So red color wavelength is satisfying this condition. If red color is satisfying this condition, so automatically red color, the same wavelength, is going to satisfy this condition also. Try to understand. This and this
Yes,
condition,
sir.
they are same.
Yes, sir.
It means red color in the reflected light, you are observing red color maxima. But here in the transmitted light, it means red color will be absent. Red color will be absent. I'm just assuming. Suppose here in reflected light, suppose blue color is absent. Suppose blue color is not observed. Blue color is absent. It means it is forming minima in the reflected light. So blue color wavelength is satisfying this condition. It means it is going to satisfy this condition also. It means in
Yes, sir.
transmitted light, you are going to get blue color fringe. You will observe blue color fringe will be observed. Fringe color will be observed.
सर
Yes, beta.
तो सर अगर देख रहे हैं मैक्सिमा में अगर रेड कलर प्रेजेंट है और इसमें ट्रांसमिटेड लाइट के लिए एब्सेंट है तो सर
Okay.
हमें वो फ्रिंज दिखेगा कैसे जब एक ही साथ एक जगह
No,
कलर
no,
रेड
no,
कलर।
no. Suppose you are having a film, ठीक है ना, in which you can observe the reflected light also and transmitted light. Suppose film is like this. So from this side you are going to observe. Suppose a film is like this. So here, from here you can observe the reflected light. From this side you can observe the transmitted light. So you can
यस सर।
observe both sides. It is not
यस
always
सर।
like this. So it may be like this. Film may be like this. ठीक है? In laboratory, you can have many experiments like this where your film is like you can place your film like this,
परपेंडिकुलर डायरेक्शन।
perpendicular
यस सर।
direction. ठीक है? So it will be. ठीक है? So you can write here. It means in reflected light and transmitted light. It means in reflected light and transmitted light, we will observe. It means in the reflected light and transmitted light, we will observe we will observe complementary colors. It means in reflected light and transmitted light, we will observe complementary colors. We will observe complementary colors. लिखिए नेक्स्ट नोट वन। नोट वन, ठीक है। फ्रिंजेस ऑब्जर्व fringes observed in thin film interference. Thin film interference are called are called localized fringes. Localized fringes are called localized fringes because they are localized within the thin film. Because they are localized within the thin film. Because they are localized within the thin film. ठीक है। Another important point is,
Sir, can you
yes,
repeat?
yes, beta, please. Hello. Because they are localized within the thin film.
Can you please repeat?
Yes. Fringes observed in the thin film interference are called localized fringes because they are localized or confined within the thin film. ठीक है। In case of Young's double slit experiment, films, those fringes, maxima and minima, they filled the complete space in front of slit S1 and S2. So they are called as non-localized fringes because they are not confined to a particular plane. Because they were not confined to a particular plane, you can move the screen in Young's double slit experiment in forward direction or in the backward direction. Everywhere, for every new position of the screen in Young's double slit experiment, you will get the pattern. So they are non-localized. They are not confined to any particular plane. But here, all the fringes, they are confined within the thin film. So that's why they are called as localized fringes. They are called as localized fringes. Second, another important thing is, okay, to observe complete thin film pattern, to observe complete thin film pattern, to observe complete thin film pattern from the single position of the eye, to observe complete thin film pattern from the single position of eye, from the single position of eye, comma, one has to use extended source. One has to use extended source. One has to use extended source. ठीक है। source . ठीक है. Extended source may be considered. Extended source may be considered as made up of. Extended source may be considered as made up of infinite number of point sources. Infinite number of point sources. ठीक है. Actually, if you are having a film like this, ठीक है, and you are having this source here. This is a point source, suppose. So what is going to happen here? ठीक है. One of the part will be reflected like this. Another part will transmit. It will move like this, and it will move like this. So here, from here, if your eye is here, you can observe this part of the pattern. But suppose your eye is here. This is your eye. ठीक है. Then you will not be able, if you are using point source, you cannot able to see this part of the interference pattern. So what do you need here? You need an extended source which is made up of infinite number of points. So it is made up of infinite number of point sources. So this is extended source. So I'm having this type of extended source. So what is going to happen? It is okay from here, whatever light is coming, okay, you are not able to observe, but there will be a point here. Out of these infinite points, there will be a point source from which light will strike this part. ठीक है ना. A part will move like this into my eye. ठीक है. A part will, so थोड़ा ठीक नहीं बना. So a part will move like this. It will be like this. Surely from this point, light is not entering into my eye, but there will be another point from which whatever light is emerging, that will undergo in this way, that will split in this way, enter into my eye, and my eye will be able to observe the interference that is taking place here. So that's why if you want to observe the pattern, ठीक है, that is formed throughout the film together, then you need a extended source like this. ठीक है. So here in this experiment, if you want to observe the complete thin film, then you need an extended source. So for today, I'm going to stop here. In the next class, I will discuss the numerical part of this, and then I will start Michelson interferometer. Okay, beta. Thank you very much.
Sir, please show the first slide.
I will show you all the slides. Beta. Just 1 second.
सर एक क्वेश्चन है, ये वेव ऑप्टिक्स खत्म होने में कितना टाइम लगेगा?
But next week I will be able to complete diffraction. ठीक है. Single slit, double slit, and grating. Not more. It will be roughly 8 classes. 8 classes.
सर
Yes, beta.
सर लियोर्स मिरर और फ्रेसनेल बाइप्रिज्म नहीं पढ़ाया जाएगा?
Pardon?
लियोर्स मिरर और फ्रेसनेल बाइप्रिज्म.
हाँ बेटा, I can teach you that thing, but if you
Okay.
look into your syllabus as well as previous year questions, ठीक है ना, then you will find out that they are not a part of your syllabus. ठीक है. They are asking questions only from Young's double slit experiment, from the thin films, from Michelson interferometer, and then
Yes, sir.
single slit, double slit, N slit diffraction or grating, and from polarization.
Yes.
So here, first I am trying to complete only those parts which are important for your exam. ठीक है. If you need that, I can provide you the videos, ठीक है ना, of this Fresnel biprism and Newton's ring experiment, ठीक है? We will provide you
यस
the
सर,
videos. You can go through that. Okay?
यस सर, यस सर।
So please have a look. So this is the first slide. Second, this is second one. Third, fourth, fifth, ठीक है? And I'm showing you more slides where questions are written. You can try to solve those questions. Six, seven, eighth. ठीक है अपना, try to solve these questions. I will discuss in the next class.
थैंक यू सर।
Welcome to